simple algebraic group.
Okay, so I'm a bit worried about the clock there. I hope I do my time correctly. Okay, so first off, I'd like to thank Britta and Gabrielle and Carolina for the invitation to speak. I'm well aware that my research is way outside of the realm of the counting conjectures. So while I did not want to occupy a slot for a long talk, I'm just too pleased to be able to have the opportunity to say a few words about my friend and colleague, Günter Melle. So I'm going to wax poetic about him for a little while before I start talking about math. Günter and I met in 1987 at a Durham meeting where Lustig was giving a sequence of lectures on the Lean-Lustig theory. We were both early career mathematicians, and at that time, and as over the years, when we met at various conferences, including the Spezies meeting that now has attached its name to mathematics, I found Günter to be a rather private and reserved person. I could only appreciate him from a distance, his achievements and his contributions measured by the numerous citations of his work and the quality of his talks. Okay, then in 2007, so many years later, we gave a 2-week summer school in Venice, and where I was completely daunted by the challenge of meeting the high standards of his lectures. Afterwards, we decided to write a book, which I hope you have all bought, based on the material in that course as we presented it. I mean, the material wasn't new. And anyway, during that endeavor, we became, I would say, true friends and collaborators. So I discovered many sides of Günter that I had not seen before, and that we had a lot of, in fact, discovered that we had a lot of similarities. So we're the same age, actually. And we both love mountains, and we both at that time loved chocolate, and we loved the precision of language, you know, yeah, the precision of language. So right early on, he tricked me before I knew him so well. He would send me back emails that I had written to him, and then he would change something in the email. And I was like, no, that's not what I said. Okay, so, and then I kind of learned to know the difference between his banter and when he was being serious. About the mountains, you know, the higher the better, the steeper the better, the colder the mountain lake, the better, you know, you get the picture. It was great having a colleague who was a friend and a colleague. I mean, somebody with his stature, but who was willing to talk seriously to me about my life as a mathematician and our children and everything else. So there are just two qualities that I want to mention. So first, that you will have all experienced, I think. So that is his generosity. I would not be surprised if at least half of the people in this room have had him, have received from him comments about a preprint or a paper that they put on the archive where he reads it carefully and sends you a list of corrections. And that's his time that he's taking for fostering what we do, and truly to be appreciated. And then the other quality is, of course, his competitive spirit in and outside of mathematics. You know, he loves to keep a tally of things, right? I mean, you go to his webpage and you see the number of races, the number of mountains, the number of visits, the altitude climb, well, you know, like that. So in 2020, when he did turn 60, there, in all seriousness, this was not a joke, he said to me, Donna, you do realize this year, I would have been the youngest person in my category in all of those races that are not happening. And I said, yeah, well, and he said, yeah. Okay, but so that's sort of, okay, another funny story, to say how similar we are. So last autumn, we went on an autumn hike, which we like to do. And, you know, we're getting old. And I said, well, I had said to myself, we're going to get to this place and it's not very well indicated on the map. And I thought to myself, if we get there and we don't see the path, I don't want to do it. And we got to that place and I heard Günter, what I heard him say was, we better go on. What he heard me say was, we better go on. And so we went on. And it wasn't a good path. Okay, anyway, I came home and my husband said, how was it? And I said, oh, you know, Günter, he's so competitive and we had to climb that mountain and I didn't want to and I was scared. Fortunately, I mentioned that and Günter said, no, you're the one who said you had to climb the mountain. Anyway, okay, so there are two events in my life which show that Günter is somehow unique in my life. And so one of those is that he's the only person, he's the co-author of the only book I've ever written. And he was part of the team of the first 4,000 meter mountain I climbed. Okay, so that makes him unique. You know, okay, that makes him unique. And so even though we're old, sort of, even though we're old, I can still hope that we have time to add some other event to our list of things that we did together. So, yeah. Okay, so now I talk a little bit about mathematics. So, okay, so the work that I'm going to talk about fits into the body of work which aims to say something about the behavior of particular elements in irreducible representations of groups, and in particular their eigenvalue multiplicities. So giving a good survey of what's been done in that area would take a lot of time. So let me just say two big lines of research and mention some names. Okay, so bounds on actually codimension of eigenspaces, codimensions of eigenspaces in irreducible representations of groups of elements, irreducible representations of groups. So here there's work of, well, you know, there's old work on irreducible groups generated by reflections or pseudo reflections, and that's actually was used in some of Günther's work. But other than that, more recent. So in 1991, Gordeev wrote something about that gives a bound on codimensions of eigenspaces. That was in characteristic 0, and then that was improved by Liebeck, Hall, Liebeck and Seitz, I think. And let me look at a date, 1992. Also a bound, these are lower bounds. And then Guralnik and Saxel in 2003, yep, Saxel in 2003. These are all results on these bounds, okay, on codimensions of eigenspaces. Okay, sometimes there are adjectives in front of irreducible representation. Sometimes the group is primitive, acting primitively, tensor indecomposably, but putting some adjectives in front, they give you some bounds on codimensions of eigenspaces of elements, okay? And then another type of result is the number. So that's bounds on dimensions, but the number of distinct eigenvalues of an element. Eigenvalues of an element, also in an irreducible representation of a group. So there, yeah. So there are results of, there's actually an old result. There's an old result in characteristic 0. I had not actually seen that paper before. That says something along the lines of if you give yourself a semisimple, an irreducible representation of a semisimple group, algebraic group in characteristic 0, and then you know that you have an element that has r plus 1 distinct eigenvalues, then it tells you something about the highest weight of the representation. So, you know, I mean, I didn't know that. And then more recently, there's work of Supernenko, Supernenko, Zalesski, and two papers, 1998 and 2000. Where they study irreducible representations of finite groups of Lie type in defining characteristic and look at elements that have simple spectrum, so elements with distinct eigenvalues, okay? And then, so simple spectrum. And then in more recent work, Zalesski and DiMartino look at a similar situation where, and I'm going to define that later. Here I'll say almost simple spectrum because I'm going to define it, almost simple spectrum. So again, you know, results along the lines of if you have an irreducible representation of a group and you know that you have an element with simple spectrum, or you know something about its eigenvalue multiplicities, can you identify the element? Can you identify the representation? Okay. I guess if you were trying to sell the interest in the results, you could say, well, okay, this might be interesting for people in computational group theory, because if you had yourself in front of you a group that had an element with a certain property, maybe you could identify it. Okay, that was not my motivation, but I guess one could say that. Okay, so that's the historical remarks. Oh, the clock is gone, so I have no idea what time it is. No, I have, it's okay. I'll just try not to, just stop me if I go too, okay. Okay, so now let me talk about what the work that I've done recently. So this is joint with Zalesski, with Alex Zalesski. And one of the papers came out last year, and one of them is in the preprint form. Okay, so our setting is that we give ourselves G, a simple algebraic group, defined over an algebraically closed field, and the characteristic can be 0 or positive. Okay, so I need to, okay, so I want to look at a specific kind of set of conjugacy classes of elements. So let me remind you probably of the following definition. So an element G and G, so recall, is said to be regular if the dimension of its centralizer is the rank of the group. Okay, and so if the element is semisimple, which is what we're going to look at, so G and G semisimple is regular if and only if the centralizer, the connected centralizer, is a maximal torus. Okay, so it turns out those will be the elements that will show up often in the talk. All right. So the work sort of starts. Okay, I have to be careful because there's something hidden here. From a simple observation about the group SLV. So observation. So in the case that the simple group is SLV, let S and SLV be semisimple. Then it's regular, then S is regular in SLV. If and only if all of the eigenspaces have dimension 1. If and only if all eigenspaces are one-dimensional. Okay, so that all eigenspaces one-dimensional, that's simple spectrum. Okay, so you might ask, well, okay, so now I give myself a different simple algebraic group. And is there a representation out there that by knowing something about the eigenvalue multiplicities of an element on that representation, it will identify whether the element is regular? Okay, so that's sort of the question. Okay, so question. For G, let's take simply connected so that we have all representations available. Okay, so for G simply connected, simple, okay, it's always the same thing, simple. Okay, simple algebraic group over K. Can we find some KG module V? Does there exist? KG module V such that we can characterize regular elements in G via the action on this V, eigenvalue multiplicities, such that regular elements, regular semisimple elements of G are characterized by the eigenvalue, well, let's say by the spectrum, actually eigenvalue multiplicities of S on G, such that regular semisimple elements S. Okay, so that would be sort of the goal. S on G. Okay, so one of the things you want to notice is that if you have, okay, so remark. I have to pay attention to the time. Okay, remark. For any representation, so let S be in G, rho from G to GLV, a representation, any. I mean, there I'm going to look for an irreducible one, but any representation, then if rho of S has simple spectrum, then necessarily, then S is regular in G. You know, because if it has simple spectrum, its centralizer up in the GL is already a torus, right? So it can't have anything other than a centralizer being a torus down below. Okay. All right. So that's the first thing you want to note. All right. So now it turns out that simple spectrum is not quite the property that we want to look at. Okay, so I'm going to make another definition. Okay, so definition. Let A be just a matrix. Okay, we'll say diagonalizable. Okay, we'll say that A has almost a full spectrum if it has at most one eigenspace of dimension greater than 1. Okay, we say A has almost a simple spectrum if at most one eigenspace has dimension greater than 1. Okay. All right, so sort of group theoretically, what would that mean in the groups that we're looking at? Is that then if you took the centralizer of such an element, the connected centralizer of such an element, then, okay, so it would be allowed, well, in SL, let's say in SL, yeah, because in SL we know what it means. So in SL, if you took an element with almost simple spectrum, then the centralizer would be allowed to have a big GL somewhere, okay, and the rest would be diagonal. So if you took its derived subgroup, then either the derived subgroup would be a simple group or it would be the identity. Okay, so there would be a group theoretic way of saying what that meant in SL. Okay, all right, so now I can state our first result that was in the first paper. So so theorem 1 is, yeah. In here? Oh. Why do you want to do that?
Well, just to have it in the
Oh, but I mean, I can make the definition in SL as well, right? I mean, yeah. I mean, I just wanted to say generally speaking what I mean. I guess. Okay, so theorem 1. Okay, so this is not such a bad characterization. So G is simply connected, simple. Okay, I better write all that. So that G be simply connected, simple. I'm not going to say algebraic group because that's what we're talking about. Simple. S and G semisimple. S and G semisimple. V non-trivial irreducible. Non-trivial irreducible. The G module could even be a tensor product here. Okay, suppose that S has almost simple spectrum on V. So suppose S has almost simple spectrum V. Then S is regular, unless and then there's a pretty short list of things that could happen otherwise, unless one of the following holds. It's one of the following. Okay, so the theorem is not a theorem unless it's precise, so let's make it precise, but at the end I'll say how you should think about it. So G is AN or BN or CN, n greater than or equal to 3, n greater than or equal to 2, DN, n greater than or equal to 4, and the dimension of V is equal to n plus 1, 2n plus 1, 2n or 2n, respectively. Okay, and you're all thinking, I know what those are. Or G is a 3, and the dimension of V is 6. Or G is C2, and the dimension of V is 5. Or G is B, n greater than or equal to 3, and the dimension of V is 2n, and P is 2. Okay, so essentially what I'm saying is S is regular unless G is a classical group and it's the natural module for G. Okay. Now, I mean, the statement has to be like this to be 100% precise. You should think of this as being D3, and that's the natural representation. This C2 is really B2, and then that's the natural representation. This is just because of the isogeny between B and C. Okay, so the theorem essentially says, that if you have an element that has almost simple spectrum on some irreducible representation, then either that element is regular, or you're looking at a classical group on its natural representation. Okay, or another thing is you shouldn't be having non-regular elements acting like that. Okay. Now, another thing, you can't really say it's the irreducible, I mean, it's the natural representation, because of course it could be twisted that. So that's why I give you the dimension instead of the highest weight. Okay. All right. Okay. So that's not too bad. Okay. So now, now that sort of then puts your focus on regular elements in representations. And really what I wanted, I mean, originally we were thinking about simple spectrum instead of almost simple spectrum. And so that led us to, actually, I should say it led Alex, not me, to, because it was based on his other work, to somehow make a definition of it that's slightly stronger than regular. Because here, this is some relationship between almost simple spectrum and regular. And you might say, well, is there some other property that's a little bit stronger than regular, as simple spectrum is stronger than almost simple spectrum? Okay. And so Alex made a definition, and then we had a really good referee for this paper, really good referee, who said, oh, you can't call it that because that already exists in the literature. And we wanted to, so Alex wanted to call what I'm going to define for you strongly regular. So how many people in the room know that strongly regular already exists in the literature? Oh, you already knew that, Martin, and you didn't tell me. Well, anyway, so Jay, I'm not surprised. Anyway, okay, so strongly regular is in a paper, is in actually Steinberg's paper on regular elements. And strongly regular is if the full centralizer is of the element is a maximal torus. So if the group, okay, because you know, the connected centralizer being a maximal torus is regular, but the full centralizer might have some other stuff outside. Okay, so he says an element is strongly regular if the full centralizer is a maximal torus. So unfortunately, that term was already taken. Okay, Alex and I are having a bit of a fight about what we're going to call it. But since he's not here today, then I'm going to call it something. And before the paper, we send back a revised version, we'll come up with something that we agree on. Okay, so definition. I sort of like this definition, this one, but I don't think he likes it. So we're, no, whatever. Okay, okay, definition. So this is a definition only for the purposes of this talk. Okay, so let's G be, I'm going to stop repeating. It's simple algebraic group. I'm going to stop repeating all this. Okay, so let G be as above, be as before. Okay. All right. So now we'll say that S, let S and G be semisimple. Okay. So I mean, really don't write this down because this is for the day. Okay. We say that S is add regular if, okay, so add regular if add of S has exactly the dimension of G minus the rank of G plus 1 distinct eigenvalues on the Lie algebraic G. Okay, now, okay, that sounds a bit technical. Let me tell you, all I'm saying is here is it has the maximum possible number of distinct eigenvalues. Okay, the eigenvalue 1 occurs for the torus, right? All the other, then you've got these root spaces, and what you're doing is saying I want to avoid that any of the root spaces have combined or that they're 1. Okay, so equivalently, if you put S in a maximal torus, suppose that you put S in a maximal torus, which you can, then S is add regular if and only if its definition would be in a maximal torus, if and only if alpha of S is different from beta of S for all T roots, alpha different from beta. Okay, so, all right. So it's somehow regular as it could be in the adjoint representation. Okay, but I mean, this is probably not what we're going to call it, but I'm calling it that for the day. Okay. Okay, so, All right, so that is stronger than regular because if your element, okay, stronger than regular. So I want to prove that add regular implies regular. So I'm going to say if it's not regular, right? So if the element's not regular, then that means that it's in the kernel of some root, alpha. So alpha of s is 1 for some root, okay? But that means minus alpha of s is also 1. So the element is not add regular, okay? So it is stronger than regular, okay? Which makes some sense to call it strongly regular, but we can't because that's taken, okay? All right, so this is something that's in between, well, I mean, it's stronger than regular. Having a simple spectrum is stronger than having an almost simple spectrum. So we can hope that we get a theorem, you know, that's kind of like the other one. But okay, so unfortunately, it's very technical and it's so, well, no, it's not technical, but the list is longer than that. So I wrote et cetera here because I don't think the actual list, you know, it's 8 items, okay, and I've given you 3 of them, okay? So that's theorem 2. So G simply connected, okay, simple algebraic group, S semisimple. Take a non-trivial irreducible representation with P restricted highest weight. Okay, so this time I'm not looking at tensor products. Okay, and suppose that this phi of S has simple spectrum. Okay, then S is add regular unless, and then there's a list. So the list is longer than just the maximal, I mean, than just the natural representations for the classical groups. Okay, it's not a real long list. Okay, there are 8 items, and you know there's a list of weights for each group. Okay, I didn't think it would necessarily interest you to see them all, but that was somehow the goal was, I mean, if you, can you say something about elements that have simple spectrum? You know they have to be regular, all right? But maybe you could also hope that they in fact have to be add regular, okay? And most of the time they do, okay? Okay, so that's the flavor of the theorem. And now there's a theorem 3. Okay, so the same thing, exactly like over there, G omega phi all that the same. Suppose that phi of S has almost simple spectrum, okay? Then again, S is add regular unless one of the following holds. Well, you'll have all those examples over there and just a few more. Here, there's just 5 more examples, okay? So it's some kind of a classification result. Probably it's not as nice, okay. Neither of these two are as nice as the first result, which somehow really does hone in on the natural representation of the classical groups, but it does tell you something about behavior of semisimple elements and representations. Okay, so now I'm just about going to quit. I'm not going to write it down, but I'll just tell you that in both of the theorem 2 and 3, then we show that the exceptions really are exceptions. You know that for every one of those, you can really go find, in fact, a regular element that behaves, that's a counterexample to the statement, okay? And so that is not add regular, but still has either simple or almost simple spectrum, okay? So they really are exceptions. And then the final thing I want to say is you might wonder, okay, how do we prove those things, all right? And let me just tell you one more result, and then we'll stop. So the main tool is the following result. And then some analysis of the weight lattice of representations, but the main tool is this proposition. So let G be simple, yeah, let G be as above. And P from G to GLV, an irreducible representation. Then the following are equivalent. There's a semisimple element. There exists S and G semisimple, such that phi of S has almost simple spectrum, such that phi of S has almost simple spectrum, and that's equivalent to knowing something about the weight lattice. That's the first statement. And 2, all non-zero weights of V occur with multiplicity 1. Okay, so those are really equivalent. Okay, even if it's a tensor product. Okay, and so once you know that, then you're led to want to classify the representations like this, which we did. Okay, so then we write down the list of weights that can have that property. All the non-irreducible weights occur with multiplicity 1. And then we have to somehow study and see what elements do in those representations. But that's sort of the main tool of the proof. Okay, so I think I stopped fast.
Thank you. Yeah, no, thank you. I like both parts of it all. Question on the second part. There's almost simple groups and semisimple elements in there. Question might also be
Yeah, we didn't look at it, so maybe yeah, that's what then we combine our disconnected and connected, yeah, finite and yeah. Maybe.
There's another question.
Yeah, actually it's related to conjectures, but yeah, okay. So it's related to Gunther's, but even maybe easier. I mean, why in theorem 1, what's the role of the simply connected? If you drop that, I mean, at least the regularity, I think, doesn't change, right?
Let G be. Yeah, you're right. I mean, well, the point, yeah. The thing is, I guess unless one of these following, yeah. So a lot of these wouldn't hold if the group were not simply connected because you just wouldn't have the representation
right.
around. So that's all. I mean, it's, yeah, that's the only reason. So you would have fewer representations showing up if the group weren't simply connected. Yeah. Okay. Yeah, that's all. That's all.
Are there any further questions from the audience?
And so you don't want to ask some other anecdote about Gunther and the number. Okay, whatever. Many. I was writing my talk and I was writing that part there and I was like, why did they ask me to talk about math? I could just talk about Gunther. Well, anyway. Okay.
Right. No. Okay. Yeah. In case there are no further questions, then let's thank Donna again. And we are basically continuing right away. Are you thinking of that?